For our last lesson this week, we're going to talk about tree diagrams and Bayes' rule. We actually made tree diagrams before when we were designing experiments. This is going to be a little bit different because we're going to have values on the branches of the tree that we will then end up multiplying. So let's take a look at when I would use a tree diagram. Here I've got, among college students, 44% are binge drinkers, 37 are moderate, 19 abstain from drinking. Now, why would I use a tree diagram for this? Because starting right here, I've got different percentages for different categories. So if you're a binge drinker, 17% of them have been involved in an alcohol-related injury, while only 9% of moderate drinkers and none of the people who abstain from drinking. So I'm going to make a tree diagram using all of these percentages, and then I'm going to come back to finding these values. So here's how a tree diagram works, and I did it ahead of time just to make sure that this video wasn't 30 minutes long. But I want you to take a look at how it's set up. From the beginning, I've got three choices. I've got binge drinkers, moderate drinkers, or people who abstain. If I add all of these up, they should add up to 1, because they're going to fall into one of those categories. Now, for binge drinkers, 17% have had an accident and 83% have not been involved in a serious accident. So again, notice this adds up to 1. Here I've got 9% of moderate drinkers in an accident and 91% not. Again, this adds up to 1. And then people who abstain, 0 in an accident, 100%, or 1 not in an accident. Now, the most important part of the tree diagram is the next part right here. Now again, normally I wouldn't show all of this work. I would probably just multiply the values and find the answer. But this is essentially finding the probability that someone is a binge drinker and has been in an accident. Notice how I found this. I've taken 0.44, which is from this branch, times 0.17 from this branch, and found my value. And then I've taken 0.44 times 0.83 and found that value. And I did that for all of them. So the questions on the last page were to find this value, to find this value, and to find this value. And once I've made my tree diagram, it's very easy to find. So now I want to talk to you about some of the more difficult probability questions you might encounter. And I want to talk to you about Bayes' rule, which is a rule that we can use if we want to do this without making a tree diagram. So looking at the first one, it just says the probability of no accident. Well, looking back at my tree diagram, the people who were not in an accident were these people and these people and these people. So of course, I can just add all of those values together, and that will give me my probability of no accident, which is 0.8928. Now, if I want to find the probability that it's a binge drinker given that there's no accident, now this is going to be a little bit different. So the probability of a binge drinker given that they were not in an accident, again, the numerator would be that it's both people who were bingers who are in an accident, and the denominator would be no accidents. So notice this value that I just found, 0.8928, is my denominator for this question, and the numerator is people who binged and were not in an accident. So that would be the 0.3652, which we had found here, bingers not in an accident. Now, Bayes' rule is another way that we can solve the same question that we just solved here, because sometimes you don't want to find a tree diagram because it's kind of a pain in the rear unless they ask you to. So let's take a look at Bayes' rule. Bayes' rule says the probability of A given B is equal to the probability of B given A times the probability of A over the probability of B. Well, let's take a look step by step in this question. The probability that binge no accident would be first the probability of no accident given binge. Well, that's just that 0.83 because that was the percentage they told us of binge drinkers who weren't in accidents, times the probability of a binge drinker, which was the 0.44 because 44% of people were binge drinkers. So that numerator is now very easy to find. Now the denominator, I cheated a little bit because I did use the values from the tree diagram that we made, but if I didn't make a tree diagram, I would have to find each of those values. So I would take the probability of no accident using binge probability of accident using moderate, etc., and add all of those together. Here's another example we can look at. So this is seat belts and injuries. So in 77% of accidents, the driver was wearing a seatbelt. 92% of those drivers, there was no serious injury, while 63, there was no serious injury. So let's make a tree diagram, which would be accident, 77 and 23, and then injury or okay, injury or okay. Again, the most important part is these four values, which of course should all add up to 1. Now, using the tree diagram, if I wanted to answer this question, the probability of a driver who was seriously injured wasn't wearing a seatbelt, notice was seriously injured, that's my given. So given serious injury, were they not wearing a seatbelt? So you would do no seatbelt and serious injury, so the intersection of those, which is no seatbelt and injury. And then on the bottom, I would put all the people who had serious injury. So who had serious injury? These people, and also the people who were belted but still had a serious injury, which is that percent. So again, I would just add those together, and that would give me 0.5842. Now, I could also do this with Bayes' rule. This time I showed all of the work. So with Bayes' rule, I would say the probability of serious injury given no seatbelt, that was given to me, the 0.37, which is the opposite of this, 0.37, the complement of that. And then the probability of no seatbelt, which was the 0.23, again, 0.23 coming from here. And then the bottom, I did the multiplication the same as before. So the 0.77, 0.08, 0.23, 0.37, that's where I got those values. That one, I didn't use the tree diagram, otherwise I would have just found that value right away. So this is the way to do it the long way. Either way, notice that I get 58.42%. Now, why do people like Bayes' rule? Well, because it's essentially a way for us to look at what one variable does, or the effect of one variable on another. So even though 23% don't wear seatbelts, they account for 58% of all the deaths and serious injuries. So we know only 23% were wearing the seatbelt, or 23% were not wearing their seatbelt, but those people had 58.42% of all of the accidents. So that's really what Bayes' rule is all about, is being able to break down two variables. Here's a question for you to try on your own. So I want you to press pause. Again, make the tree diagram, find the probabilities, and then answer the question that says, is this a good testing method? And then press play to check your work. So the first thing I should do, of course, is to make my tree diagram. And in this one, we're saying this is 1 out of 5,000. You just had to turn that into a decimal on your own, 1 divided by 5,000. So women with cancer is 1 out of 5,000, or 0.0002. And then not women that don't have cancer, 0.9998. Next, we're looking at the test correctly detects ovarian cancer in 99.7% of women. So that means if they have cancer, 0.997, that's when they get a positive result and they do have cancer. The people who have cancer that have a negative result, so the people who are misdiagnosed, very, very small number. So far we feel like that's a really good test. Now, if you get a false positive, that's 5% of the women, which means these women don't have cancer, but they get a positive result anyway, or positive or no cancer with negative result. We're hoping that this number is very, very high. So again, if I'm finding the probability of cancer given a positive result, so I'm actually trying to calculate, given that a woman is given that, hey, you have cancer, do they actually have cancer? That's what I'm going to calculate here. So that means the probability of positive and they have cancer divided by the probability that the test was positive. So this value comes from right here, people who have cancer that have a positive test. The denominator is the people who just had a positive test, which is these two values. So that gives me a total probability of 0.00397 or 0.397%. So less than a percent. So what does that tell me? Well, that means that over 99% of the time when a woman is given the news from her doctor that she has cancer, 99% of the time they're wrong. And only, 3.397% of the time they are correct. So maybe not a great method. Of course, yes, it does detect it correctly most of the time, so maybe it's not bad, but then maybe let's do a second test before we tell women that they have cancer.